Let's go ahead and get started. Okay, I want to talk to you about something called the Pareto power curve. It's a very interesting probability density function. I'm sure that you've all had probability at some time in your life, and you're familiar with what a probability density function is. Pareto was a guy that he did a lot of stuff. He had Pareto optimization and the Pareto front. He was the one that noticed that when you design something, there's usually trade-offs. So there's something called a Pareto front, where if you're trying to buy a safe car that is cheap, cheap cars aren't safe and safe cars aren't cheap. So there's a trade-off that you have to have. And Pareto was one of the first to recognize this sort of trade-off. Another thing he did is he wanted to model stuff like, the distribution of incomes. And that's where the Pareto thing initially came in, distribution of incomes. And the density function is given by the f sub x here. And you can see that it's kind of cool. But what it does is it talks about the minimum that a density function could take, and then it defines the probability density function for that. Now, if you take the logarithm of both sides, you get what is shown here on the second line. And then if you plot the log of fx versus the log of x, you get a line which is going down. And this line goes down a lot. So this is a log-log plot of the probability density function. And this is referred to as a power curve. And the power curve represents a lot of things in nature. One of the things is income. Down here we have people in Haiti. I don't know how to spell Haiti. Let's just do Haiti. Okay. Up here, very, very rare, you have like Bill Gates. I don't want to do that. I hate it when a computer thinks it's smarter than you are. Okay, here you have um, here you have somebody like Bill Gates. Okay, and up here you have somebody like Elon Musk, right? And I don't know. I'm here somewhere. So this is what we would talk about in terms of income. This was Pareto's original idea, but actually it's descriptive of a lot of phenomena and a lot of distributions that we have in the world. For example, size of cities. You have a lot of small towns. My wife was raised in a place called Farmersburg, and if you look at the city population, Farmersburg has a really small population. And there's lots of cities that are very small towns. I live in McGregor. McGregor, Texas has one traffic light in the whole city, one traffic light. So that's a small town too. So Farmersburg, and I think probably McGregor is a little bit bigger. But then you have places like, I don't know, Akron, Ohio. And then you have the big cities. You have the Los Angeles, you have the New York City. So if we were to look at the population of all the cities in the world, it would probably follow a power curve. Isn't that interesting? Another thing is avalanche. I think it's spelled right. Okay, an avalanche is that every time a piece of a snowflake drops, it displaces a few snowflakes until it gets to the point where it breaks the camel's back. And it breaks the camel's back, and you get an avalanche. And so you have the small displacement. And then down here, you have the avalanche that occurs every once in a while. So the power curve is descriptive of a number of phenomena. I read a book called Ubiquity, and the whole book, Ubiquity, was about the power curve. And I had never seen that before. The interesting thing about the power curve is that the Pareto distribution is sometimes it has an infinite mean and an infinite variance, believe it or not. It's just one of these weird sort of distributions like a Cauchy that can actually have an unbounded mean and an unbounded variance. But nevertheless, apparently it's something that occurs in reality. And there's many density functions that occur in reality that are weird in the sense of having an infinite mean or an infinite variance. So with that, let me share my screen and show you what I tried to do. And this was my introduction to swarm intelligence. What I wanted to do is I wanted to generate a avalanche, and I wanted to do it in the following sense. Let me share my screen. So here was the idea. I wanted to see if I could simulate an avalanche. This isn't swarm intelligence per se, but this is kind of testing out the Pareto result. So what I did is I dropped a piece of snow or a pebble or something like that on this stack. And then if anything in the mountain was lower than that, it started to fall down the mountain, but it only fell down the mountain when there was an empty space there, when there was a space which was lower. And I got the following interesting result. So what happens? The avalanche is as follows. You can see the piece of snow kind of hitting in the middle, and then the degree of the avalanche is the time between a couple of pings in the middle. So you see ping, 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 ping. And if there's a long ping, that means a lot of snow has been displaced because it takes the same amount of time for that to happen. And so that was kind of interesting. So I'm building a avalanche here. At least I thought I was building an avalanche, and let's see what happens. Well, this is what happens intermediately. So this is a young pile, and now we're starting to have more profound avalanches, if you will. So that's very interesting. And then the cool thing is that there's a steady state which occurs, which I didn't anticipate. But here's the steady state. Now, in the steady state, this mountain is built on a square, if you will. And if a piece of snow falls outside of the square, it just falls off the scene. So you can see in many cases that the square actually, or that the piece of snow actually goes down and falls off the edge of the screen. So I wouldn't expect here a Pareto. I don't know what I would expect. I didn't know what I would expect here. So if you look at a sequence of the fallen pieces of snow, you get the following sort of histogram. So we see there was a little avalanche here, a little avalanche here, a lot of little stuff here. And I don't know, I was kind of disappointed. So this is the number of grains of sand. I guess I did sand instead of snow. The number of grains of sand that were toppled in each iteration. And I did 10,000 of them. And then I did a histogram. Now, if I did a histogram and did a log plot of the histogram, I would expect a power curve. Well, I didn't get a power curve. I got this. So it turns out that there was a lot, there was a few little ones, and there was kind of an average. But I think at least the right-hand side is kind of looks like the power curve in the sense that the right-hand side goes down. So I was disappointed in that, but I thought I'd share that with you because that's kind of fun stuff. And here's the way that the grains of sand or the snowflakes reach a steady state. You get the number of sands, and then up here you get the place where it starts to fall off the edges. And That's kind of cool. Okay, so I just wanted to share that with you. That's very, very, very quick, and hope you enjoyed it. It's not really swarm, but it's kind of interesting. Now, I was asked a question, I think it was by Gabriel last time, about one of the projects he was doing, which was actually being done with electronics. And he had some very curious results. And it reminded me of the game of life. The game of life is essentially a digital swarm. In other words, it's a swarm which occurs on a Cartesian map of squares and obeys some simple rules. So with that, I'm going to share this with you. I'm going to share with you the game of life, the incredible game of life. Here's the idea. You have either a cell on the checkerboard on or off. If it's on, it's considered to be living. If it's off, it's dead. And here are the rules, which a guy named Conway did, and he developed it actually using a checkerboard before computers. First of all, there's underpopulation. A living cell, that is a cell that's on with fewer than two live neighbors, dies. So you have to have at least two live neighbors in order to keep on living. Number two, a living cell with two or three live neighbors lives on to the next generation. So if you have two or three live neighbors, you have a family and you live on. Then there's overcrowding. A living cell with more than three living neighbors dies. So you got the problem in the city where too many people are living around you. And reproduction. A dead cell with exactly three living neighbors becomes a living cell. There's kind of a resurrection, if you will. So a dead cell with exactly three living neighbors becomes a living cell. It kind of gives birth. Now here, these are just very simple rules, a lot like Swarm. Swarm has very simple rules. This has very simple rules. So here's one which is called a still life. This is a block. If you have four live cells denoted by the black boxes here, it does turn out that that just stays the same. So nothing happens. It's following the four rules of the game of life, and it just stays there and it happens. On the other hand, if you have three live cells in a row, it becomes a blinker. It goes from three horizontal to three vertical, back to three horizontal, back to three vertical, back and forth. So it just sits there and blinks. That's according to the rules of the game of life. And then there's some more complex things like a glider. So up here you have a glider. You have, let's see, one, two, three, four, five elements. According to the rules of life, this manifests itself next as this pattern, which manifests itself as this pattern, which manifests itself as this pattern, which manifests itself as this pattern. Now, what is really cool about this is that this pattern is exactly the same as this pattern, except displaced horizontally 45 degrees. So if we repeat this again, this glider is just going to go down 45 degrees and just keep on going. That's the reason they call it a glider. And so this again obeys the four simple rules of the game of life, Conway's rule of life. So with that, I would like to share with you an incredible video. I've made a link of it available on YouTube that shows what you can do with the game of life. And let's see what you can do with the simple four rules. The game of life is an infinite two-dimensional orthogonal grid of square cells, each with one of two possible states, alive or dead. That's the reason it's called the game of life. Um, here we have the case where it has eight neighbors totally. A square is surrounded by eight neighbors, and they are horizontally, vertically, or diagonally. At each step in time generation, the following transitions occur, and we're going to see a repeat of the four rules that I gave you initially. And here are the four rules. These are just restatements of what I talked about previously. So you have overcrowding, you have family, and you have birth, if you will. This last one is reproduction. Okay, here's the stuff you can do. This I think is the best video for the game of life. First of all, you see the glider. And here's what's interesting. There's a configuration where you can make a glider generator. And this glider generator is bouncing back and forth. You will notice, by the way, the four squares are not telling each other. And then you have a couple of gliders manufacturing a glider manufacturer and another glider manufacturer aiming at each other. And when the gliders meet in the middle, they annihilate themselves. Or you can have a glider thing and it just generates it into infinity. Here's something more complex that actually builds a so-called spaceship using the four rules of the game of life. And so this is a factory that manufactures a bunch of spaceships. Here's another interesting one. I'm not sure what it does. I think there's actually some configurations which allow it to be a computer. I find it just mind-boggling that people would spend their time coming up with these different things. This is an interesting one. It actually generates spaceships, and here's an annihilation. This is a really fancy oscillator. Here's another fancy oscillator. It just comes back and repeats itself. And another pair of fancy oscillators side by side. Here again is a manufacturing plant that takes a couple of small spaceships and makes a big spaceship. Here's generating I don't know, what is that? That's generating a bunch of stuff, bunch of letters. I don't know if you saw that last one, but everybody just annihilated themselves. Here's kind of a percolation. Oh, there's in your face sort of thing. There's a big, big, long one. Don't forget that the sheet is kind of infinite, if you will. Here's one thing attacking another. There's something else attacking each other. Here's two guys that join forces and send out ships in tandem. So we have a chase going on here. I have no idea what this is. This is a spaceship that leaves a plume behind it, if you will. Yeah, and here's a fascinating spaceship that leaves behind a cloud of smoke. Here's another manufacturer that generates a glider. Here's a here's a glider generating stuff. And there's a small glider that actually generates fumes. Oh my gosh, this looks like insect aliens, doesn't it? There's some gliders, if you will. So just with those four simple rules, you can do amazing stuff. And again, there's hobbyists. There's a site, I forget what it is, but there's a site where people get together and try to come up with fancy ways of incorporating the game of life. So this is an equivalent to a swarm, a digital swarm, if you will. Now, some of you might have heard of Stephen Wolfram. Stephen Wolfram, if you want to do integrals, you go to Wolfram Integral or what's the other one? Wolfram Alpha or something like that. And he's the one that did Mathematica. Mathematica is an incredible symbolic mathematics package. And the guy is really, really smart. Even before Mathematica, if you wanted to know anything about Mathematica, you went to the web and you looked for Stephen Wolfram because he probably had something that dealt with that mathematics. He kind of knows everything. Well, one of the things that Wolfram did is he wrote a book called A New Type of Science, where he looked at the cellular automata, and he looked at different rules. I mean, we have the four rules of the game of life. I think that you can see that the rules that you can have with the game of life are just are very limiting. There's a bunch of different rules that you can have, and he began to step methodically through the different rules that you could do and see what happened. And he wrote a whole book about it. Some of you might know Dr. Keith Schubert. How many know Dr. Schubert? Everybody should know Dr. Schubert. He's at one time he did rare life sort of things. He went down in a sulfur cave, for example, and this was funded by NASA. Why would NASA send you down a sulfur cave? Well, they were looking at extreme life. And there is life which exists inside us, inside a sulfur cave, and they were investigating it. And one of the things Dr. Schubert tried to do is come up with a game of life set of rules by which this very elementary life could exist and repopulate. And the reason this was done by NASA is kind of a hand waving thing that they said, well, this is really cool, and maybe we have life on other planets. And if we do, and it's an extreme environment, maybe that life will be the sort of life that we see in sulfur caves. By the way, if you want to search for it, Dr. Schubert was featured in a issue of National Geographic where he went down into the sulfur caves. It was such a cool idea, and he did it jointly with some other people. So that's all well and good. Okay, so therefore we have covered the ubiquity, my attempt to generate the power curve, which was a failure, and we've also come up with the game of life and talked about the fact that the game of life has a number of variations that you can look at. And Stephen Wolfram did this in his book, A New Type of Science or A New Kind of Science. I forget which one it is. Okay, with that, let me talk about search in general. Everybody here is design stuff. And design is something wherein you take your domain expertise, you apply it to a problem. And typically, the first time you apply it, it doesn't work. You have to go back and you have to tweak it a little bit, sometimes more than otherwise. This is basically an idea of search to get an optimal design. Okay, who can tell me what this is? It's very apropos to this time of year.
That would be a pumpkin.
And what is the
Is this
circumference
pumpkin
of
pie?
pumpkin pie? That's right. Because the ratio of the circumference to the diameter of a circle is equal to pi. So that's a nerd's way of saying pumpkin pie. You like that? It's pretty cool. Okay, so with that, let me talk about search. And this has nothing to do with search. It's just kind of funny. Uh, this is a book that was published by William Dembski, And William Dembski is a good friend and just a genius. I mean, the guy, he has more degrees than a circle. He has a bachelor's in what is it, psychology. He has a master's of divinity from Princeton, and he has a master's in statistics, and he has a PhD in mathematics, and he has a PhD in philosophy. So I call him a paradox because he has two ducks. That's my joke, a paradox. Okay, so he wrote this book, and this is one of his seminal works. They just released with Winston Ewart, who used to be a Baylor student here of mine. They just generated a new version of this book, The Design Inference. In this, he was a mathematician, and he looked at design from probability standpoint, and that's what we're going to do now. And I wrote with Bill Dembski and Winston Ewart a book called Introduction to Evolutionary Informatics. And there is a short course which is available, and that there's a link to that on the web. It's totally optional, but it's a nice short course on evolutionary informatics that covers the contents of the book, Evolutionary Informatics. What is evolutionary informatics? It explores the information requirements in design in general, and specifically applies it to evolution. So let's talk about, first of all, evolutionary computation. And that's the claim of design. So if one looks at the Darwinian side of evolution, you have survival of the fittest, you have repopulation, you have mutation, and then you repeat. Survival of the fittest, right? And in other words, you kill off the weak, and you do repopulation, and then you do mutation, and then you repeat. And this has been accepted for a number of years. And one of the bad things about Darwinian evolution is that Darwinian theory is the impact that it has had on society. You had, for example, the eugenics movement, where different races were thought to be inferior to other races in terms of because of genetics. If you want to watch a great video, watch Human Zoos by John West. It's available on YouTube and it's free, but it's a fascinating story of eugenics. And Margaret Sanger actually started Planned Parenthood on this premise that she wanted to control the population of the least fit. Indeed, during World War I, there were German generals that said war is very important for the survival of humanity. Why do we have to have war? Because we got to go war with each other because there's going to be survival of the fittest, and war kills the weakest. So it seems to me that everything, at least socially, that Darwin touches, it kind of spoils it. But this has nothing to do with whether it's a science or not. So let's talk about whether it's a science or not. Again, survival of the fittest, repopulation, and then you repeat survival of the fittest. So here is kind of a block diagram. You start with a set of possible solutions. This can be random, or if you have domain expertise, it can be close to your solution. And you go to a computer model and then you say, how good is each search? So we're talking about evolutionary computation now, which is evolution on a computer. It did turn out in the 1950s that the biologists got all excited. They said, now we can prove evolution. We can prove evolution because we have a computer. We don't have to go through millions and millions of generations in order to talk about the fruits of evolution. We could do it on a computer and we can have a generation like that. Unfortunately, that is what we're going to talk about now and why it works. So this is evolutionary computing. You say a set of possible solutions up here on the left. You go to a computer model, and this computer model usually is what eats up most of your time because this computer model dictates how good your solutions are. So you have to figure out the survival of the fittest. And in order to do that, you have to figure out how good each one of these possible solutions is. And once you do that, you get how good is the solution. And then what you do is you keep a set of the best solutions. In other words, you kill off all of the weak ones. And then you begin to duplicate and mutate. And sometimes they have something they call crossover. We're not going to talk about that. That was a very contentious debate at one time whether you should have crossover, but we're not even going to address it. And then you repeat this. So we have next generation, survival of the fittest, repopulation, and mutation. And it goes on and on and on. And what this is this is a search. This is a search, at least in engineering circles, for a specific type of solution that you're trying to get a possible design. Now, there's lots of very interesting books on evolutionary computing. Here are a few. Um, when I was president of the IEEE Neural Networks Council, now the IEEE Computational Intelligence Society, I was approached by this man, David P. Fogel, whose father had actually pioneered the idea of evolutionary computing. And David said, we need to start a journal. And indeed, we did start a journal, and I'll talk about that in a little bit. And so I pushed forward for the journal on evolutionary processing. So you can see there's a lot of books that are associated with evolutionary computing, which is applying the concept of evolution to computer design. In fact, one of the most celebrated cases is this little antenna here. This looks like a little twisted paper clip stuck in a cork. But this was designed iteratively by computer and was actually manufactured and placed in a NASA spaceship. It was designed to have a frequency of one type. So going back to here, the thing that killed this was the set of possible solutions. This is the design of the antenna. What are the solutions? That's probably where the paper clip is bent and the angle that it's bent. And so you can think of a number of different parameters that you have to tune in order to get the result. The computer model was a thing that ate up the time in the computing of this, because you had to go to a model of electromagnetics and look at the geometry of the antenna, and from the geometry of the antenna decide how good it was to receive the frequency that it was being designed for. And so this chewed up a lot of time, because it's a lot of number crunching in order to determine the fitness. And then the other parts are pretty straightforward. We have a ranking of how good they are. You keep a set of the best solutions, duplicate and mutate, and then do a set of possible solutions. So that's the way that this antenna was generated. And indeed, for most, okay, I'm looking for my iced tea. Oh, here it is. Okay. For most evolutionary computing, this is exactly what you've done. Notice that in this case, we do have a fitness associated. That fitness was how well does the uh, how well does the antenna perform? So we have a goal in mind. This is contrary to Darwinian evolution, where they talk about just unguided development. There is no guidance. There is no final goal. So this is one search algorithm, and there are many, many search algorithms. Here, by the way, is the IEEE transactions on evolutionary computing that David Fogel started. And if you look at his introduction of the guest editor, you'll see that he thanked me for helping him get it started. And I think at the time it was a good thing. It probably is still a good thing. It's still going on, and people are talking about evolutionary computation. Now, everybody comes up with a set of algorithms for design. And here is just a list of a few that I have. Evolutionary computing is one type of design. There's Ant Connolly optimization, artificial immune system, a bunch of stuff. And what you do is, in order to get your name known, you come up with a search algorithm. It used to be in the area of operations research that you could come up with a new search algorithm, and everybody would say, wow, you get your PhD because you got a new search algorithm. And the big battle back then was, well, my search algorithm is better than your search algorithm. I was actually privy to that. One time we published a paper comparing artificial neural networks to CART, classification and regression trees. And we looked at a number of different problems, and we found out that neural networks actually work better. But we could not make the claim that neural networks work better always. The only claim that we could make is that artificial neural networks work better on the problems that we considered. And there's other problems where the cart would have worked better. This was actually emphasized in a 1989 paper by Wolpert and McCready called the no free lunch theorem. And this was an astonishing result because it was a big smack in the face of all the people that were trying to design their own algorithms. And here is the thing. If you have no domain expertise about what you're trying to solve, unless you can make prior assumptions about the problems you are working on, then no search strategy, no matter how sophisticated, can be expected to perform better than any other. Wow. That means that you cannot claim superiority of any algorithm to perform best in all cases. And this was one of the things that people were trying to claim in terms of defense of their search algorithm. They showed that their search algorithm was better in certain cases, but that didn't mean it was true across the board. To David Fogel's credit, he published the no free lunch theorem in the Transactions on Evolutionary Computing by David Wolpert and William McCready. And Wolpert is the main guy. I believe he's at the Santa Fe Institute right now. And they wrote in their original papers, no free lunch theorems indicate the importance of incorporating problem-specific knowledge into the behavior of optimization or search. In other words, if you don't have expertise, and where does that expertise come in? That expertise comes in determining which things are the most fit and also the initialization. You can come in with the initialization with things that are, closer to the solution than would be normally if you just choose the initialization randomly. So here is what somebody else wrote. I had correspondence with this guy. If a search algorithm, it says if a search algorithm performs better on all cases, then it is like a perpetual motion machine. The no free lunch has shown that it's like a perpetual motion machine. So the no free lunch theorem says that no algorithm, including evolutionary search, is better. And conservation to generalization performance precludes it. Now, he wrote this in 1994, so he recognized this problem initially, which was very good. By the way, here on the bottom right, I have my idea of a perpetual motion machine. Can anybody identify how it works? You start this wheel spinning and it will spin forever. Okay, you ready? See this nine? If you start it going counterclockwise, when this nine gets to the bottom, it will become 6 pounds. And when this six goes to the top, it'll be 9 pounds. You get it? Okay, I got a few smirks. I didn't get any chuckles, but I thought that was a very clever perpetual motion machine that I had created. Yeah, so the nine becomes a six and the six becomes a nine. Really, really cool. Of course, that doesn't happen. Now, I don't know how many of you have heard of Formula 409. Anybody heard of it? Okay, so you have heard of, you know why they call it Formula 409?
Does it take 409
It took,
tries?
that's right. We mentioned that design is inherently iterative. You get a result, you make it better. You look at that, you make it better. And Formula 409 was perfected after 409 tries. Same thing with WD-40. Now, WD-40 is done by a chemical engineer named Larson, and it took him 40 times, 40 trials to come up with WD-40, this water displacement center, the water displacement liquid. And that's what WD-40 means. It means water displacement system found in 40 different iterations. Now, notice that the requirement of domain expertise is paramount here. If Larson did it, it took him 40. If you had a high school chemistry student do it, we might be calling that WD 4006, right? Because he didn't have the domain expertise. It would be more trial and error. So the more domain expertise that you bring to a design problem, the better the results are going to be. And this is something which, if you think about it, is pretty obvious. Design expertise, intelligence is required for design and search. There has to be an intelligence. Let me give you an example. We saw a bunch of search algorithms. Suppose that we had the following. We have We have this lock which goes between 0 and 9. And I don't care what your algorithm is. The chances of opening this lock in 5 tries is independent of the algorithm used, right? You can I There's just no way that you can apply any algorithm to get that lock opened better than any other algorithm. It is totally something called a blind search. Now, what the no free lunch theorem did is it says that, yeah, everything is requires domain expertise, but it says without domain expertise, if you go into it totally blind, then what happens? Okay, here it is.
Nope. Is this it? Nope. Is this it? Nope. Is this it?
No, George,
Okay, this was a true blind search. I mean, the guy that's sitting there on the bench is blind, and he has a Rubik's cube, and he's going back and forth and saying, "Is this it? Nope. Is this it? Nope." That is the epitome of a blind search. By the way, this is taken from a movie called UHF. I think it's UHF, by starring Weird Al Yankovic. So if you're interested in the movie, there it is. It's the bottom from the movie UHF. Okay, let's take a look at a blind search. Again, with the no free lunch theorem, a blind search, if you know nothing about what you're doing, should be as good on average as any other search. Now, it doesn't say for a specific problem that one search is not going to be better than another one. It simply says if you know nothing, choose any search that you want to, and it will work on average as better as any other search. So let's look at trying to find the phrase "methinks it is like a weasel." This is a story from Hamlet, where Hamlet is looking at the sky and looking at clouds. And he says, somebody says, "Well, what does that cloud look like?" And he says, "Methinks it is like a weasel." So that's what we're going to do. And we're just going to do random search. We're going to choose random things from the alphabet. And we get this. And just like the blind guy, we said, "Is this it?" No. Choose some more. "Is this it?" No. "Is this it?" No. "Is this it?" No. So finally, we will get to the point where there is a probability that we will get to "methinks it is like a weasel." But you can actually figure out that it takes 1.2 times 10 to the 40 queries. In other words, you would have to do 1.2 times 10 to the 40 queries in order, on average, in order to get this. You could actually talk about a Bernoulli trial, and you get a success or not and figure it out that way. And if a query occurred, if you have 1.2 times 10 to the 40 and you did 3, it turns out that if we did it in terms of microseconds, so therefore we did a query every microsecond, that would be 10 to the 26 years or 10 to the 23rd centuries. So that ain't going to work, is it? With domain expertise, with the blind search. Is this it? No. Is this it? No. Rather, we need to have some domain expertise. And many of the people that use evolutionary program put in domain expertise to help them get the right result. Suppose you're looking for an Easter egg in the state of Wyoming. That would be basically a blind search. And you probably wouldn't find it for years and years, because the only thing you could do is probably an exhaustive search. And I don't know, maybe somebody's moving the Easter egg. But if you do have somebody who knows what they're doing, that person can say, if they know the location of the Easter egg, you're getting warmer, you're getting colder, you're the same. So this is what Riley was talking about. So we think methinks RT, methinks RS, and then we get down here and this S becomes a T. Whoop, we're moving away. So we're getting colder. And there can be the same. We can get exactly the same sort of distance, if you will. And by the way, you might think, well, you have a good oracle. No, because you could have that person in Wyoming. If we look at the last line, they can have bad oracles, and they can lie. And you can't choose an oracle at random. It has to apply to the problem you're looking at. You can have an oracle wherein it says you are getting colder when you're getting warmer and warmer when you're getting colder. And in that case, if you get a bad oracle, it will tell you the wrong way to go. And because it tells you the wrong way to go, it'll actually take you longer. So on average, you're going to be just as well doing a random search if you have no domain expertise rather than choosing a warmer, colder oracle at random. And there's other types of domain expertise. One is called the Hamming oracle. And the Hamming oracle, named after Hamming, Bell Labs, and you're probably familiar with Hamming windows and Hamming error correction codes. Well, this is the Hamming distance. And the Hamming distance is how many things you have wrong. So methinks the RT at the end is wrong. So therefore the Hamming distance is 2 since you have 2 incorrect. And if you keep on handing down the Hamming distance, you get a better and better result. If you keep decreasing the Hamming distance. So eventually when you get to the solution, it should have a Hamming distance of 0. So this was actually looked at by Bill Dembski and me in the conservation of search algorithm. It turns out that the no free lunch theorem said that if you didn't have any domain expertise, that you could not choose the optimal search. That one search on average is as good as any other search. Well, Bill and I took it a step further, and this has been a very nicely cited paper. And it says, well, not only that, you can do that, but if you do choose with domain expertise, you can choose an algorithm which will work best because you have domain expertise. You know, you have some background on what you're doing. And so we were able to actually measure the amount of information that goes into the search and measure it in bits. For example, back here, I think that the warmer colder oracle probably has less information than the Hamming oracle. And so maybe you get more bits of information here for the search than you do here. So we'll talk about that in information theory if indeed you're interested. So here's an example of the idea of active information. What is active information? Active information is the way that the difficulty of the search is reduced when you introduce domain expertise. So here we have a case. This is a binary switch, and there's 10 switches there. And in order to get the right combination, you need to get all 10 switches right. So that's 2 to the 10th. That's 1,024 possibilities. So every chance is 10 to the 1,024. You could do this in an exhaustive search. And by the way, don't ignore exhaustive searches. If you can do an exhaustive search and search all combinations by just leaving your computer on all night, go ahead and do it. It's a lot better than applying a search algorithm that might save you a little bit of time. Your computer doesn't care about sleeping. It can work all night. So with this one, I would literally try if I could give it to a computer. I give it a try and say, try all 1,000 different combinations. But this is for illustration. This is pedagogical. Okay, so this is 10 bits of information. The difficulty of the search is 10 bits. That's the difficulty of the search. Somebody comes in with domain expertise and says, you know what? I know that the last 3 placings are 101. So the domain expertise tells me the last 3 bits. So all of a sudden, my difficulty decreases, doesn't it? It decreases from 2 to the 10th to 2 to the 7th. So it reduces 1,024 to 128. So therefore, by this domain expertise, we have reduced the complexity of the design problem by adding this active information. Now, in this case, the active information is very obvious because we can just carve it out in terms of bits. In general, it isn't. So remember I talked about in the 1950s, everybody was really excited about evolution. All the biologists, they said that, my goodness, we can do things now which are just incredible because we can do a lot of generations on a computer, the time it would take biology many, many eons to do. So there's been a number of different algorithms to do this. And one is at evoinfo.org, and I gave a link on that. I want to show you some things from evoinfo.org. First of all, the idea of a blind search. Now there's different searches that you can do. You can do unassisted random search. You can do proximity search, which means that you're using a Hamming oracle and you're actually using offspring. You're doing an evolutionary computation here. So you have a number of offspring. So you have a solution. You get your different you get your different fitnesses from the Hamming distance, and then you kill off the weak, you keep the strong. And so this is going to give you a lot more information. So for random search, we have something called weaselware because me thinks it is like a weasel. So this is unassisted search. It will not work even for moderately sized problems. And monkeys at a typewriter eventually creating the complex work of Shakespeare is simply impossible. And we'll get to our definition impossible. Is it probable? Yeah, but no, it's impossible. And we have the methinks it is like a weasel, and we talked about the probability of that occurring, and that is just nothing. And we can also have different types of searches. This is done in um, using the Hamming oracle and then using the Hamming fitness in order to determine how fit something is. Notice in the blind search, we have no idea of how fit something is. And down here are the other oracles that can be used. So let me go to the actual software. This is kind of interesting. This is the simulation where we can do an English phrase. So let's do, methinks it is like a weasel. Or a rat. So I'm increasing the thing of the length of what we're looking for. So first of all, there's partition search, and partition search is simply looking at a result and seeing if it's better or not. If it's better, you keep it. There's nothing good or bad in terms of evolution, in terms of a population. So for partition search, you look at a solution and then you make a change. This is sometimes called stochastic descent. If the result is better, then you keep it. If the result is not better, you discard the change, go back to your original and try something else. And so this is taking into account the history, but it's a Markov sort of process because you only look at what you did the previous result. There's a deterministic search. Now, what the deterministic search is actually incredibly simple. You simply go through the alphabet. You go through A, where's the A's, where's the B's, where's the C's, and what you find out is you always take 27, a minimum of 27, I'm sorry, a maximum of 27 queries in order to do that, because you have to go through the 26 letters in the alphabet plus the space. And then there's unassisted random search, which is the blind search. And let's just do these. So I'm going to go up here and I'm going to hit the start search, and we'll see things happening here. So you can see that the deterministic search got it, like I said, in 27. It just checked and it did very well. If you look at the partition search, where it kept the best result, and if you mutated it, it got and it was worse, you discarded it, went back to the original, mutated it again, and this converged at 106 queries. But we have down here the unassisted random search, which has no domain expertise at all, is going to go on forever. And the median number of queries here is 6.33 times 10 to the 52. So that's kind of crazy. So there's other iterations that you can look at, and I'm not going to go through those. We'll just go through the ones we're talking about now. Okay, so you can see that with domain expertise, it's kind of obvious that you get great and wonderful results if you know enough about what you're doing. That's it. That's what I wanted to present.